unfortunately. So the two things I want to talk about with respect to self-propelled droplets are essentially the manifestation of synchronization and navigation. Before we start, I need to thank the people who did all the work, which are in red. So essentially all the old and the new graduate students, undergraduate students. We have a very strong student community at IIT Bombay. Some have moved on, some have stayed back. And this is my perpetual collaborator from Toulouse, Veronique, and my former student when I was in Mexico, but now he's a faculty member, Jose Manuel. So this is the workhorse for today's talk. So it's essentially a pentanol drop on the surface of water. And the moment you put it, it just starts moving. And it moves back and forth because it's in a closed configuration. And the question you ask, of course, is why does it move? The uniaxial motion is due to the confinement of the setup. So, but the motility is what we wondered about. And the mechanism seems to be, as Pompa in her talk quickly mentioned, the Marangoni effect. So what happens is, in a utopic world, the pentanol drop would eject little droplets homogeneously all around. Since the effect of pentanol is like a surfactant, it lowers the surface tension in the vicinity. So if the ejection is uniform, there will be a global lowering of the surface tension in the vicinity of droplets, and nothing will happen. But we all know that in realistic situations there are fluctuations. So there is an inhomogeneous distribution of the droplets ejected from the big drop in the vicinity of the big drop. So for example, in this case, on the left hand side there are more drops. So consequently, the surface tension would be lower there, and it gives rise to an unbalanced force, hence movement towards the right hand side. And as it moves away from it, it encounters more fresh water, higher surface tension. So it's like a positive feedback mechanism. It starts moving till it reaches the boundary or something else happens, right? So there's a net force due to this, and this, to put it succinctly, so the motility by virtue of the surface tension gradients is provoked by spatial inhomogeneity of surface pentanol concentration around the drop. This is also called in some corners of the literature as the solital Marangoni effect. This is also due to temperature, but this is predominantly a solital Marangoni effect. A beautiful manifestation of us. Unfortunately, we could not have the privilege of seeing that yesterday, was the teardrops of, we were clicked for a moment that we will be able to, I actually wanted to do the experiments for the students, unfortunately no. So what happens here is, if you have an alcoholic beverage of your choice, beer would not work, single malt is very good, wine is very good, red wine is even better. Yeah? Sorry?
How many students do you have in that group?
9, including postdocs. We still, yeah. No, but the point, it would have been, I mean, anyway, let's not talk about things which are not feasible, right? So what happens here is, so it's a mixture of alcohol and water, right? There the meniscus, the surface area is more, so the evaporation of alcohol is faster, so you're left with more water, so the surface tension here is lower than in the bulk, and it defies gravity and starts to move on. So you start getting these drops, right? Eventually the weight will catch up, it will fall down or it will stick there. This is again a rather exquisite manifestation of Marangoni effect. Another one Pompa really breezed by, which he showed. So to put it clearly, sometimes it's better to give you a coherent picture. There's a transfer going on between two phases due to the surface tension gradient. Unfortunately, this does not help you tell whether the alcohol or the wine or the scotch is high quality. It just tells you whether it has more alcohol, which sometimes is therapeutic, right? So which is good. So this is an experiment I strongly recommend under favorable circumstances. Okay, but here the nonlinear dynamics kicks in. So I'm going to show you some synchronization of these droplet behavior in a particular geometry. See, the first known experiments done on synchronization was this Dutch physicist who also worked in optics back in the 17th century. So he was ordained, correct me if I'm wrong, by the royalty of Netherlands to come up with the most precise pendulum clocks, right? And he set up this experiment. If I believe the fable, he was unwell at that time on a ship, and he came up with this, and he set up 2 pendulum clocks, started them within a reasonable error, and what he realized after a while, that either these two started synchronizing in anti-phase oscillation, or it started doing in-phase oscillations. And he realized that it's due to the fact that the 2 rhythms were talking to each other via the mechanical vibration of the common beam. So this was the first known experiment done on synchronization. Then it went to a latency period for a couple of years, and then it came back with a vengeance when people started to go out, because synchronization essentially implies convergence of dynamics. Chaos implies divergence of dynamics. People came up with chaotic synchronization, which sounded like an oxymoron, but it does work, right? So to put it technical terms, this transfer of information could be various ways. First, the most common in the nature is bidirectional coupling. So you have one oscillator, omega 1, the other one, omega 2, not too far away, and they mutually adjust the rhythms to converge to a common frequency, which is somewhere in between. This is called unidirectional coupling, which is more observed in geopolitics and human relations than in nature, right? In which the one person says, you need to do this thing, and the other person like a slave. And it's actually appropriately called master-slave relationship. So there's a change of frequency of oscillator 2 to converge to the frequency of omega 1. So omega 1, nothing happens. It doesn't get any feedback from this omega 2, but omega 2 does all the work. There is another interesting manifestation wherein the oscillators need not be coupled at all. But nonetheless, they are subjected to a common fluctuation. So they both synchronize. During the course of this talk, I'll hopefully be able to show you the first 2 manifestations of these phenomena. So now here I will be to do an Indian improvisation. Mike. So these are metronomes. You guys hear it, or should I? No, at the back, man. So each metronome has started, and it's doing its own rhythm. And after a while, they start synchronizing. So what has happened is essentially same as in Huygens, reverse. Here the bass you see seems to be moving. So there's a global coupling between the oscillators, and each one adjusts its rhythm and comes to a common frequency for all of them. This is ensemble synchronization, and it's quite exquisite if you do it. You can actually do it with 2064 and stuff like that. Also, when you go to a concert and people start clapping and the performance is very, very good, they keep on clapping for a long time, and what happens is the clapping becomes rhythmic clapping, as seen in the baseball games in Korea and Japan, right? So what happens is each person is clapping, is listening to the other oscillators, other human beings that is, yeah, and subconsciously adjusts its rhythm, and they converge onto a common rhythm. And it has been clearly shown in countries which have less heterogeneity, like the Eastern European countries, the phenomena is very well pronounced. In countries like Brazil, it's different. In India, we don't make it work because we don't want to make it work. So it will never happen, right? We go against that. The last example, just to show you, it's not just cute stuff that we do. I don't know how many of you are old enough to remember the year 2000, the Y2K, the British with the pompous act that we're going to open a bridge, and they called it the Millennium Bridge. They should have learned from the bridges that we have in Varanasi and stuff like that. And soon after, when the bridge happened, you see all the people subconsciously while walking in synchrony. And this was, you see that? You can actually see the global wave going left and right. And it was completely shut down, and typical, the explanation that was given was, this was due to an under-researched phenomena. It did not matter, it was discovered 200 years before that, right? And they said that the lateral sway had an unconscious tendency to match their footsteps. It's synchronization. So this is just to motivate. The synchronization is not only fun, exotic, and to demonstration purposes, this has technological relevance as well. Okay, so back to our mundane third world country cheap tabletop experiments. We have a very beautiful rectangular quartz board which has these dimensions. Outer, these are the inner dimensions. What I want you to notice is that we make a floating linear channel. It's just a laminate sheet, that the dimensions of that almost match the inner dimension of the board. So it's a very tight fit. So we put it very carefully. So it's floating, yet it does not move due to the constructions of the geometry. And then we put a solution of water, and as I showed in the workhorse, a pentanol drop. Ferroin is for visual purposes, and we put an initial amount of pentanol so that the gradient is not too much between water and pentanol, and the drop doesn't break up immediately on impact. So this is, yet again, as I said, you should focus on these dimensions. So this is what this looks like. We track it. Being nonlinear dynamicists, we turn it into time series, and actually looks like a beautiful, robust, repetitive P-Raven oscillation when plotted like this. This being the position. Then we said we want to study synchronization. We need at least two oscillators. So this is the first thing we tried. So in this case, this scale is just for visual purposes, to give you a visual aid. So if you look at this here, so the first drop goes from 1 to 4, and the second drop goes approximately from 5 to 8, right? And there's come close, and then they go back. So this is an anti-phase synchronization. Also confirmed by the fact that if you plot the Lissajous figures, it goes on the 135. Yes, ma'am.
Yes, thanks. I was wondering if you've looked at the shape of the droplet. It has this really interesting crescent shape.
Yes, it does.
Almost looks like
and I'll tell you why it is. Yeah. See, okay, very good point. You make me go back a slide. I should have pointed it out here, so thank you so much for that. So you see, when it's a crescent shape, the top, the front part here, the ejection is less of the pentanol. So the surface tension is more. So it's the direction in which it moves. And then as soon as it flips over, the size changes. So there's a one-to-one correlation between the way the moon is shaped and the direction of motility. And it cannot remain circular. It always takes the shape depending on in which direction it is moving. Okay.
Have you made a model of this? It looks really...
Ma'am, no. I'm actually, contrary to this guy, there will be no equations and there will be no modeling. This is purely experiments, and people are We modeled with simple Yukawa potential. We did not go into the geometry. Just a cartoon model to see it works. But no, we are hardcore experimentalists. Now he's just mad at me because I pointed his name. Yeah. No.
I was going to say that this is a fun little sort of tabletop version of your attack illusion of your motion.
Okay. Sure. All right. There's a lot of good, cool things you can do with it, right? So this is what I already showed. Yeah. So you see, this is anti-phase synchronization, and this is this I should point out seriously enough. It's bidirectional coupling. So each drop is affecting the other. Okay. Then you go into 3 drops. The better you get at handling the experiments, you do 3 drops. And this is what we call relay synchronization, in which drop 1 and 2 are out of phase, 2 and 3 are out of phase, so consequently 1 and 3 are in phase. This is called relay synchronization in the literature. So if you look at the Lissajous figures, minus 45 or 135 degree line and the 45 degree line. So this is called relay synchronization. To reiterate, 1 and 3 are in phase, and drop 2, 1, drop 2, 3 are out of phase. This is another set of experiments in which 2 subgroups seem to form, and each subgroup shows a anti-phase synchronization. This is another motion in which you have a 4-drop configuration again, but it shows a different move than the previous one, and it actually shows a relay synchronization. But we wanted to see unidirectional coupling. We could not make coupling purely unidirectional because we can't stop the process of communication in one direction, but we can do it asymmetric coupling, right? So we take a big drop and a small drop, and the claim is that the big drop will effectively push the strong drop because it will have more coupling strength. And sure enough, I don't know whether it was clear from the video, so I'll play it again. You get in-phase synchronization. The small drop always follows the big drop. Okay? We did more experiments with this, but they're just nitty-gritty and not much. I just wanted to focus on these ones. Okay. Nowadays, so in the previous set of experiments, the coupling was longitudinal. Yes, sir. Rajesh, yeah.
When the big drop is moving,
Correct.
behind it the concentration of fentanyl is high.
I mean, behind it is
Higher than
no. In front, right? Is moving in the direction of lower sulfur. Behind it, the concentration of pentanol is higher. Yeah.
Higher.
Yeah. Sorry. Yeah.
the small drop sees a higher concentration of fentanyl in the front.
Correct.
And why is it?
But it has its own field that is emitting. It becomes inert. It does not get affected. It just follows the big one. Okay.
But is it
So-
through Marangoni effect or some other effect?
Sorry?
Is it Marangoni effect or something else?
It's mainly solitary Marangoni effect, but we don't change anything else. But essentially the effect of one dynamics on the other. Okay. So then we started doing transversal coupling. So in which now you'll see the drops moving along in the vertical, and the coupling through the solution is in the horizontal fashion. So this is ongoing work. Nonetheless, I'll show it to you. So if you have two such channels, right, the same thing remains, and each one shows its own dynamics. And when you, of course, plot the Lissajous figures, it's all over the place.
So how do they couple?
I'll tell you. Yeah. So what we do is now we make it one. If I could show you here. So now they have a common solution. They are just restricted in their channels by fish nylon wires, and the surface, the liquid inside can flow from one part to the other. Naturally, not due to we are forcing or anything, just by natural camphor dissolution. So if you are a little charitable with me, so this is the case when there was no coupling. So each one did its own. So here there is some feeling. So what we have seen up until now, they seems to switch between going in phase and anti-phase. We don't know the reason. It's just an observation. That's why I said, and this is for maximal coupling, because they're open. They can talk to each other through the solution. They're just restricted by Fishman inverse. Okay? Does everybody get the spirit of this experiment, right? It works. Then, of course, now we are trying to do it with 3, although we still haven't finished the set 2, 1. And if you have 3 such channels, both 1 and all of them, 1 and 2, 2 and 3, and 1 and 3 have no correlation between each other. And again, if you have to be charitable to me, you'll see there seems to be relay and then it destroys it, but this we have to refine more. Since it's a conference, I took the luxury of just presenting results which are of.
How do you control the coupling strength?
We go binary, 0 or 1. There is no, we have tried it with partial coupling by blocking these areas, but the results are really atrocious. Even with 1, it is not that good. The tangential coupling, transverse coupling doesn't seem to work properly. But I mean, we still haven't given up on the 3 system. Okay. You'll have to tell me how much time I have.
You still have another 7 minutes.
7 minutes. Okay. So that was the synchronization part. Then we said, okay, do these, because I've heard in this conference also, you can use these things for drug delivery and stuff like that. It's too fancy, but I think I'll show you that we can navigate using these things, exploiting the Marangoni effect. So again, be patient with me, and if I don't explain it clearly, the setup, come back to me and ask me right now. So we make now lamination treat 2 type of channels. One where all the widths of the 3 arms are identical. I mean, to the best of our experimental, these are actually students cutting stuff and doing it, right? So, or sometimes laser printer, lately we have been able to do that. So these are identical, and here we intentionally make one of the arms wider than the other one. So you see? Okay, so this is all 3, A, B, C are 0.5. Here A is B and C are still B and C are still 0.5, and this is 0.4. So we have intentionally induced an asymmetry. And we want to see, is the system able to detect that as silly little drop of pentanol on the surface of water. So first thing we did 50 experiments. Each experiment takes about 3 hours, right? So people, the theoretician come, I need to do 500. Okay, but we just want to make a point here. So in this case, it goes to, you start here, it goes to the decision point, and we saw that 60%, which is 30 trials, it went to the one on the left, and 20 times it went to. So we established a null hypothesis. We say, with a confidence level of 95%, that there is no preferred path. And indeed, for this case, we find from our data that you cannot disregard the null hypothesis. We do the same experiments, but now with the asymmetry introduced, and it seems to go, it actually goes more times, 80% of the times, to the wider channel. The reason is intuitively clear, I think, because there's more water here, there's more volume there. So let's assume that the ejection of the molecules is almost same on both the sides. There's more volume of water there, so the less lowering of surface tension, so it's a higher surface tension area. So from the decision point, this is the preferred path. But of course, it's not 100%, because there are some initial velocities, some polarization, which can affect. So in this case, we just it's like a first passage experiment. Once it goes to an arm, we stop the experiment. We don't review the path when it comes back and stuff like that. Okay? So in this case, you see that the wider channel is preferred, and you can neglect the hypothesis. We actually have a toy model for this also, so if you want to have a look at it, you can have a look at the paper. And then we did something even more cool, I think. We just put one of the drops and locked it with a fish line here. So this is like chemical asymmetry, right? You have a drop here that we put, you have a drop here, and we see that we did 30 experiments, and all the time it went to the arm without the drop. Evidently again, because here the surface tension is much lower, because the concentration comes from this little driver as well as this little neighbor, and here the surface tension is higher, the drop goes away. Okay, so we didn't have to do any H0 analysis here because it was 100%. We did it 30 times and it works all the time. So then I was teaching this classical mechanics course to the master's student, and there you have this path minimization, right? So then we said, okay, let's try this with our with our drops. So we set up, we did the same things, but we couldn't do now work with the drops because they were just breaking up. So we said, okay, like Pompard explained yesterday, we made paper disc, A4 paper, and we infused them with pentanol and camphor. The procedure is the same. You put it in ethanol and water, the ethanol evaporates, and you get this paper. And then we went to the machine shop, got these fancy gadgets made, right, in which one of them has two parts, the smaller and the larger, and then they have three parts, right? And these are aluminum blocks. You put them on the surface of water, and then this is all where the reservoir of water, and I'll quickly show you the camphor and pentanol. So it always escapes, but in these videos it escapes to the shortest path. And the results were, for when there were two options, larger and smaller, 80% with the camphor, 88% with the pentanol, it did path minimization by itself. And when it was three options, 68% took the shortest one and 74% took the smaller one. So the reason why that happens, right? That is the question. Why does happen? So if you look at, let's do it simpler in the two option experiment. This is the smaller part, this is the larger part. So all this is sink, right? So that's the surface tension of water. Here, again, assuming the ejection is more or less symmetric, this is the low surface tension area. But now the length comes into the picture, right? So you have one surface, T1 here, T2 here, but the force with which a drop is pulled would be larger towards the smaller part. Yet again, it is not perfect because of the experimental details, because there is pull from both the sides. Yeah, but there is a preference of pull due to the simple, the gradient equation. Yeah, I'm done. I'm just almost done. Yeah. So just to put it clearly, coherently, just read it out. Spatial distribution of camphor pentanol molecules in the L-shaped gel after the actic disc is placed at the center of the channel. The yellow area is the low surface tension area because of the deposition of high amounts of camphor and pentanol, and the blue area is just the water, is the sink, right? But also we assume that the concentration vanishes by the time it reaches over there, so this essentially has surface tension of water, and this is a high surface tension area. So the gradient due to the simple, the force from which the element is being pulled from source to the sink is larger along the smaller length. So this is just the statistical analysis, establishing the 95% confidence interval and being able to eliminate any statistical ambiguity, and it is actually done by the by the simple logic of solitary Marangoni effect. So we were wondering if this could be used to target a particular, I don't know, I don't want to say medicines and all that, like at least it can detect an inanimate object due to Marangoni flows a preferred path. And with that, I thank you for your attention, and I'll take any questions.
Questions? We have enough time for questions.
Hi, Puneet.
Hi.
I mean, it's very fascinating the way it kind of finds the path. But do you think it will go beyond, let's say, one fork? So if you do 2 forks, 3 forks?
It did not.
Okay.
It did not.
But you have a model, you said.
Yes.
So can you try it on the model?
Model, it works.
Okay. So in principle, it will solve a
Yes.
maze.
Yeah. The problem is at least in the pentanol case, the saturation takes place very quickly. So by the time it goes through the first barrier, it essentially has the same concentration throughout. So the gradient vanishes. That is the biggest problem. Pentanol is very, very volatile, right? So as it is, camphor it persists for more, but the coolest thing we wanted to do, Sitavra, was to solve a maze.
Right.
Right?
Right.
Up until now, we have failed marvelously on that. And it's amazing because the model works like a charm. Even if you put noise on it, it works. So sometimes I believe what my advisor used to say, that the difference between numerics and experiment is more in experiments than in numerics. So it does not work at all. And we are flabbergasted. But it does not work. I mean, maximum 2, but we cannot, but we have not given up. PhD students are supposed to suffer a little bit. So yes.
If I can just make one comment,
Sure, yeah.
you remember that the Turing patterns were, for example, very difficult to see until someone figured out that you can use a catalyst to actually trap.
Absolutely,
So
the silver, this one.
Can
right?
you use a trapper here for the?
I haven't thought about it. We haven't thought about it. Yeah, but yeah. So yeah, this is again. We just we did this year actually, and so there's lot to be done. But when Abhishek entered, he said, "Oh, we'll do the maze," and I'm still waiting. Yeah. Anyway, yeah. But I know the experiments are very hard, and the thing is, I don't know. People don't appreciate that 50 experiments is like almost 30 days, and if good with theoretician, let's do 100 more. You can't do that. No. We have a shelf life, Sorry. These people trivialize everything, right? Yeah. Any more questions? Thanks.
Probably another theorist question. So what happens if you take many drops on the surface without confinement? Can you get it to flock? Can you do it any?
Oh, you didn't see the poster?
Sorry, I saw the triangles, but
Yeah.
I didn't see the droplets.
No, we did, droplets we haven't tried because, as I said, droplets are very, even for these experiments, I hope I was able to convey the message, these are not droplets, these are discs. Droplets are very hard, they're like a pampered child, you have to treat them very, very carefully, because otherwise they drop, they break. So no, we have not. Our best hope, and I think if you have seen Abhishek's poster, is that we do get some competition between Cheerio's effect and the other repulsion, and we do get some kind of flocking, but we have not tried it with droplets. Is going to, I don't know, it's going to be very, very hard.
Speed at which these drops move, is that like dependent on how big the drop is? Because it would have to depend on the surface area, because
And
that's how
also
fast-
the activity, right? Pentanol moves much faster than camphor.
Yeah, I'm assuming for the same thing. If you
Yeah.
have a bigger drop versus small,
Yeah.
it didn't look like that when you had say 2 drops of different size. In terms of their frequency, is there actually a difference? Frequency meaning how fast they're oscillating.
It is there, but maybe it's not that substantial because you're in a confined geometry.
Right.
Yeah, if you if you just leave it on a big reservoir, because here you have confinement, so this saturation takes faster. But there is definitely a velocity difference between the two. I can't hear you, sorry.
How long do these oscillations last for, or how long do the drops live for?
Yeah, good. Again, the answer to that is 10 minutes, but that is not the relevant point. The question you should ask is how many oscillations do you get? That is more important, because there are experiments which have a frequency of gigahertz, right? There 1 second is enough. So we have at least 200 plus 250 plus oscillations before the system starts to dissipate and then eventually start. So.
Thank you.
Okay, if there are no more questions, let's thank Punit.
Yeah, thanks. Mouse I took. Thanks. पानी मिलेगा? हाँ? Mic, sorry.
Okay, the last speaker of the day and of the conference is Tom, and Tom will be speaking about causation from correlation and fluctuation analysis. Tom?
Thank you very much, and thank you most of all to Arnab and Pinaki for organizing this nice conference and giving me a chance to say a few words here as well. So maybe 2 words about myself. I started out in physics many years ago, did a PhD and initial postdoc in mathematical physics, working on analysis of fluctuations and Goldstone modes in things like Bose-Einstein condensation and quantum spin systems. But then at some point I felt I wanted to do something a bit more practical. I was hopeless with experiments, so I could never have done the kind of nice things we just saw. And then instead I ended up in bioinformatics and computational biology. But now very recently I've been drifting back a little bit towards physics again. It could be the onset of a midlife crisis, I'm not sure. And basically, so what I'll present today is very preliminary work. It's just sharing some thoughts and ideas of things that I started working on basically 4 months ago when I arrived here for my sabbatical. I have no students yet to thank because I've not dared to engage anyone in things that may or may not lead to something. So it's just some initial thoughts and ideas, and if you have feedback, I would very much appreciate. So just for a little bit of context, we've heard a little bit already about signaling. Once you dive into molecular biology, you very quickly arrive at these kind of things. So gene regulatory networks. These are kind of models or representations of the inner working of a cell. Each of these variables here represents a gene. A gene encodes for a protein, so protein is produced. And then, say if you, for instance, focus on this one, you get a protein, and that protein itself will then affect the rate at which other proteins are produced. And this is how you get this whole cascade of events. They're particularly important in developmental processes, so how you go from a single cell to multicellular organism. But they also play an important role in the kind of signaling that Massimo was talking about. So as a model, they are fantastic. Like you can almost read them the way you would read a computer program. The problem is that this is only one part of one network. And these things take like years and years and years of experimental work just to tease out what are these individual interactions, who is controlling whom, and how does it all work. if it's in development, you can argue we only need one per organism of interest. That might still be doable. But then if you talk about signaling, each of our different types of cells in the body has a different type of signaling, so these networks are all different. And we have about several thousand different cell types just in our own human bodies alone. So then it becomes completely impossible to do this systematically, map these networks experimentally. And so for about 20 years, there's been this idea that maybe can we take a sort of computational shortcut to this problem of mapping these circuits in the cell. And the idea is, rather than experimentally manipulating protein by protein, you just observe what the cell is doing under a wide variety of inputs. So it's a bit what in engineering is called reverse engineering. You have a system, you want to understand the inner working of a system, and you just observe how it responds to multiple different types of output, different types of input, and from the output, hopefully, you can reconstruct the actual inner workings. And then you have this kind of various algorithms that try to achieve this. And so we can ask ourselves, but this is just some quotes from two very recent reviews where they had a sort of broader look at this field, and conclusion is basically that this kind of forecasting of what would happen for unseen experiments is not really working very well. So especially here, capture causal relationships from perturbation assays. This is exactly the question you want to answer. So you want to be able to tell an experimenter, if you do this experiment, if you translate that a little bit in what is happening in this field, I believe, is that we are drowning in a sea of methods and really starving for good models. And that's where the physics might hopefully come in a little bit again. So my own thinking in this area has been influenced quite a bit by actual experiment. And this is precisely what we are hoping to do in this field of reverse engineering gene networks. So rather than one by one doing the experiment, perturbing your genes, seeing what the effect is, you would hope that you can actually compute the result by just observation, so without having to do the experiment. So how does it work? Many of you will be familiar. So you have a response matrix which tells you what is the average change in, say, a variable, in my case genes, number k, if you perturb a gene, other variable at time 0. And then the fluctuation dissipation relations, they tell you that you can compute this response matrix exactly from a 2-time correlation function in equilibrium. So you have some variable here measured at time 0, and your response variable measured at some later time. So in theory, if we leave aside the question of whether equilibrium is a good approximation or not for the cells, this is telling us exactly what we need to do our program of reverse engineering. So why after 20 years is it not working? This is something you would, for instance, if you just measure how the cells, you just measure the values, say concentration of proteins in your steady state, and then you just estimate the distribution. So we don't, in a way, we don't know anything. So it's all about estimating from data. So the reason why this has not been applied or not been used in molecular biology is that if you want to do this estimation, you obviously need time series data. And this is just an example showing what it's doing. So here is it's from the same paper, simple simulation where we have 3 variables. So X is controlling Y and Z. And then there's a back interaction from Y to Z. Here it shows the correlation between Z and Y. So the correlation function, we don't see any influence of the epsilon, but then in the response function, which is plotted here, you see that as you increase the value of them, you get the bigger peak. So it's a difference between correlation and causation from response. Earlier this conference, proliferation is really the sort of a hallmark of what cells do. So every cell wants to divide. Strictly speaking, that's only true for bacterial or cancer cells, but nonetheless, proliferation is really important. And many of you, so most who work in active matter, you might have seen this perspective from about a year ago, which is discussing exactly why proliferation is important and should be studied in active matter. So I think Massimo briefly mentioned we ignore proliferation in the models for now, and Silke also mentioned briefly in passing that we can kind of deal with it. I think what this paper is arguing is proliferation not of cells, but in this case of species. But proliferation, this kind of division and evolution, is really intrinsic at essentially all scales of biological dynamics that you might be interested in. So where does now the whole idea coming in of why could proliferation tell us something about time? Basically, think of a very simple example. So we start with a single cell. It divides into two daughter cells, which divide and divide and divide. So you get this kind of proliferation tree. You have a bunch of cells alive at the end. And now imagine if you consider these two, say two sister cells. These two cells will be quite similar to each other because they have a recently dividing. So for instance, in this case, they share the same mother cell. But if you compare, for instance, this cell to this one, their most recent common ancestor lies much more distant in the past, and therefore these cells will be much more different from one another. It's the same thing as in a family tree where you would be more similar to your brother or sister than you would be to a distant cousin. So it's the same idea here. And so the hypothesis is basically that if two cells are close to each other in the tree, their similarity or their correlations would be equivalent or reflect short time delayed correlations, whereas cells that are spontaneously rather than in response to external pressure. And the idea here is basically that sometimes if a bacteria has a spontaneous mutation early in this tree, what is called a jackpot mutation, then sort of all the descendants would inherit that mutation, and such a clone would be potentially highly resistant to then later on challenging by a virus. And basically the two competing theories, whether mutations arise spontaneously without challenge or only after a challenge, would give rise to different statistics, and therefore if you measure these different, it turns on, but it sort of fluctuates very rapidly between on and off. Then it switches on maybe early on, but then it switches off again, and there's never any chance to build up a large proportion of on genes. But if the switching between on and off is very slow, then what may happen is a gene switches on early in the tree, because the switch off takes very long off pattern. This is what the real data looks like. So these are genes, so variables that are what they call non-heritable. So in blue you see a distribution of like a noise control. Sorry, in pink it's the noise control. In blue it's just a variation across individual clones. And here you see that some of these genes that are heritable show a very high variance across clones and a very sharp peak in the just the steady state distribution. Whereas here they are actually completely overlapping. So what I want to do is build a very simple model for this kind of experimental setting, and then see if we can use it for the purpose that I started with, this reverse engineering of networks. So what is the model? It's the simplest possible model where we take fixed cell cycles or fixed generation times. So it's like a clock where every unit of time, the cells that are alive at that time, they divide into daughter cells. It's run up to a certain number of cell divisions. And in the end, you have an exponential number of cells alive depending on the number of cell divisions. What matters for us is that if you look at an ancestor that divided at time k, the number of offspring here is again exponential in this time difference. So the longer ago, the more descendants it has. The final thing is if the activity, so the gene expression
okay,
of
so
those. The original go on or off. Variable, so you have here a rate at which the particle or the gene is pushed back to its steady state value. The half-life of the fluctuations is log 2 over this parameter. You have an additional variance from random fluctuations, and then the steady state value, which we can set to 0. You will know that the distribution of this random walker, it decays exponentially back to the steady state. So the steady state is where, in this case, we've set the center to 0, and it's normally distributed with some steady state variance. And the steady state variance is just the ratio between contribution from the random fluctuations and then here this drift parameter. And you also see immediately that it would not be enough to look at steady state distributions because we have start with the same value, but afterwards they diverge. And so the correlation here between daughter cells is only due to their shared initiative. So remember, the thing that we want to explore is whether we can say something about time-delayed correlations from this kind of correlations at the end of the process. And in this model, this is completely trivial. So you can compute on the one hand, so suppose you have a single realization of that process, and you check what is the covariance between the initial state and the state at some later time t. And then, of course, it's standard calculation. It gets exponential decrease of the correlation with rate alpha. So over time, the correlations decrease exponentially. Now suppose that you have, instead of one, you have two independent realizations of the process, but with the same initial value. Then we get something that was also used in the talk by Satya a couple of days ago, where these two things are not independent, but they are conditionally independent given a third variable, and that third variable independent of two random variables that started with the same initial state. In two different branches, yeah. And the factor of 2 here is also easy to understand. So if you just follow the process forward, you will say from the black one here, you follow forward one time unit for your time-delayed correlation. In this case, if we compare those two, we first have to go back to the ancestor and then forward to the other one. So we double the time, and therefore we get a factor of 2 here. Now, in the experiment that we have, remember, we don't have access to individual cells at the end of our process. The only thing we can measure is their total fluctuation, so we just measure. So I don't measure individual cell values. I only measure the total value of a gene at the end in a single clone. But then you can work out what this variance is, so the variance of a single clone. And after a bit of work, so you just group together cells that share the same common ancestor with the cell of interest, and the result in the end looks like this. So you can write, or you can compare the variance. So imagine you have, in the experiment, they start with about 50 single cells. Each of these cells is grown to a separate clone, so you have 50 clones. In each of these clones, you measure the total concentration of all the genes. And now you ask, what is the variation? in total level across your 50 clones. So you have 50 numbers, and you can simply ask what is the variance or standard deviation across these 50 clones. There's also a separate measurement where you take data not from clones that are derived from a single cell, but just a random mesh. In the random mesh, variance is simply the steady state variance, or you have the clonal variance, and the ratio of those two is a simple function of this rate parameter. And this is really what I call this fluctuation dissipation relation. So it's again the same story as the classical one. So you have an expression for a non-equilibrium parameter, which is the rate at which fluctuations decay back to equilibrium. And you can express it completely in terms of equilibrium fluctuations, in this case fluctuations that are measured at one single time point. And then there's this interesting phenomenon where you see correlations, they decay over time. In this case, they decay with respect to the age of the common ancestor. But at the same time, there's the exponential explosion due to proliferation, where if your common ancestor is older, you kind of share more cells that had that common ancestor. And so then there's a balance between this exponential increase from proliferation and the exponential decrease from the decay of correlations. And then depending on the value of this parameter, or depending on its half-life, you see that either one of those two terms is going to win. If the half-life is bigger than, in this case, 2 cell cycles or 2 generation times, then you see this exponential increase in this ratio. So you see that the variance that you compute across clones from single cell is exponentially greater than what you would get as a variance in the steady state. And this is this phenomenon which in this biological paper they called memory or transcriptional memory. So the memory refers here to the fact that the system remembers an early fluctuation away from equilibrium, because you fluctuate away from the steady state, and then there's this explosion due to proliferation. And if the fluctuation goes back to the steady state slow enough, then it kind of the whole clone remembers this initial fluctuation. But for our purposes, it basically means if you can estimate those two numbers, you can estimate this parameter, and you don't need any time series data for it. So this is where the having this phylogenetic tree information becomes equivalent